Hello, and welcome to Let's Talk Tech with DeepCore Data. I'm John Brewer, the owner and founder here at DeepCore, where we're using education to help companies make the right tech choices. In this series, we're discussing at a technical level how the internet works.
Once upon a time, there was a dark age in the kingdom of computers. Computers were chained together by the evil of wired connections. Long-distance communications were spoiled by the limitations of repurposed phone calls. Other realms were downtrodden by the woes of incompatibility. For many years, the users of the digital world waited for a hero.
Systems online.
Sometime in the early 1980s, there were a wide variety of physical networking standards for sending information from machine to machine. It was a bit of a mess. Today, we still have a lot of standards for sending information wirelessly, but when it comes to high-speed hardline communication, there's really only one game left in town: the long-lived Ethernet. Developed in the 1970s at the famous Xerox PARC laboratories, Ethernet has outlived other standards to become part of everyday computing. It's the phone cable-looking thing that plugs into computers, at least for now, but the end of cabled connections is a story for another time. In past episodes, we talked about how IP packets were routed over long distances, but we skipped over how those packets actually move from one physical machine to another. In many offices, wired connections still provide a faster, more secure way of moving data. So how does your computer send a packet to the switch? And how does the switch send that packet on to your coworker's computer? Ethernet uses its own addressing scheme, known as the Media Access Control, or MAC address. MAC addresses need to be unique to every device on the local network, and although they are usually set at the factory, most network cards today allow you to change the device's MAC address to fit your network needs. For those of you with more interest about the Ethernet frame, you can look up the IEEE 802.3 specification. So while a protocol like IP has the packet, Ethernet has the frame. Now, the frame is a much simpler form of communication, where IP packets have 13 fields and Ethernet frame has only 6. They are the 6-byte destination, the 6-byte source, an optional 4-byte tag, the 2-byte ether type, or the length of the packet, the actual payload of the packet, and the 4-byte checksum. Now, the source and destination addresses seem pretty self-explanatory, but there's an important note about them. The sender address is always the original sender of the frame, not the most recent router like you would see in IPv4. As an IP packet moves across the network, for example, it would be moved from frame to frame each time a router redirects it, but each of those frames will keep the source from the last frame. The practical upshot is that if an IP packet travels across the whole world, passes through dozens of routers, the frame that it arrives in at its destination will still have the source MAC address of the machine that originally sent it. For a moment, we're going to skip ahead here to the ether type size field. To make sense of this field, we need to go a little into the history of the Ethernet specification. Early on, this field was just the size. It told the receiving device how many bytes to read off the link before it reached the end of the packet. Very simple, data is data. In the 1980s, when DeLoreans and time travel were the norm, Ethernet 2 framing also came down the road. The major change with Ethernet 2 was identifying the content of the frame. By allowing the infrastructure to know what kind of information it was sending, we enabled all kinds of new efficiencies. Since there were only 5 fields at the time, and all of them were essential, the new protocol was like a parasite, usurping the size field for its own encoding. Why the size field? Let's investigate. The original 802.3 standard specified the maximum length of an Ethernet frame's payload to be 1500 bytes, but the 2-byte size field could contain numbers up to 65,535 bytes. To maintain backwards compatibility with all the Ethernet 1 hardware already out there, the Ethernet 2 specification declared that all the codes for these new content-identifying numbers had to be higher than 1535. The additional 35 bytes are to deal with possible ambiguities over padding around the frame. So if the ether type size field is 1500 or less, that's just the length of the data in the frame. If it's 1535 or higher, it's a code telling the receiving device what kind of information is in that frame. If it's between 1500 and 1535, then it triggers the apocalypse. Those codes aren't in use. So, for example, the ether type code for IPv4 in hexadecimal is 0800. For IPv6, 86DD. For ARP, 0806, and so on. I know that there are some people at home all but jumping out of their chairs now, asking how the receiving device could possibly know the length of the payload from a static code. Does every switch in the world need to know where in an IPv4 packet to find its length? What kind of sloppy coding is this anyways? But no, there is numerical trickery here. You see, I left out one key element. Ethernet 2 cheats. At the end of the frame, there is an end of stream signal. With the old 10 base T networks, it was a specific waveform on the line. With 100 base T networks, it's a special end of stream delimiter payload. Every physical layer, or type of cable, that carries Ethernet 2 has it. It's basically a sound, and it tells the receiving device that it's reached the end of a frame. There's one other strange thing about the Ethernet frame. There's an optional field in the middle. So the nagging question of all time, what is that field used for? Well, to explain, we're going to have to go back to the ether type field. You see, one of the ether type content codes just says, I'm a tag and the real ether type is behind me. If hexadecimal 9100 appears in the ether type field, that actually says the 2 bytes after me are a VLAN identifier, and the 2 bytes after that are the real ether type code. Pretty neat, huh? But what's the point? VLAN stands for Virtual LAN, and that's a topic for another video altogether. In general, it's a method for allowing multiple different networks to share hardware without sharing traffic. Moving on, next we come to the payload. Now, the payload is the actual data that the frame is transporting, the IPv4 datagram, the ARP packet, or whatever. The interesting thing about the payload is, unlike anything else we've seen so far, it actually has a minimum length. For regular frames, the payload's minimum size is 46 bytes. The minimum is 42 if it's tagged. Why is there a minimum here? The short answer is that long ago, when Ethernet originated, engineers needed to make sure the frames were big enough that they could reliably detect collisions on the network. It's less of an issue today, but the specification remains in the rare cases somebody plugs a piece of antiquated hardware into a network. And at last we come to the final 4 bytes, the cyclic redundancy check, or CRC. Now the CRC is a computed value that, when combined with the rest of the frame, always yields this particular output. If you plug your frame into the CRC function and you don't get this number out, you know that your frame was corrupted in transit and needs to be resent. So that's the basic Ethernet frame, or how devices on the local area network talk to each other. I did not authorize this.
Having defeated the digital foes of incompatibility, our hero fades into the annals of time. For now, the network is a better, faster place. But one day, not long from now, a new hero will rise to replace the old.
I hope you enjoyed this episode of How the Internet Works. If you like what you saw, please subscribe to our channel. And if you have questions or ideas for future episodes, leave a comment below. I'm John Brewer for Deep Core Data. Thanks for watching.